Three boiling water reactors at Fukushima Daiichi Nuclear Power Plant operated normally until 1446 JST on March 11, 2011. External power was lost as designed during the 9-magnitude earthquake. Emergency diesel generators started automatically. Primary cooling systems functioned correctly. At 1527, tsunami waves exceeded the 5.7-meter design basis, flooding emergency power systems and disabling ultimate heat removal. What followed was not a single accident, but 3 simultaneous failures of identical reactor designs under conditions that exposed fundamental assumptions about instrumentation reliability, cooling system robustness, and the independence of defense in-depth barriers. Operators responded according to training and procedures, yet each decision moved the plant further from recovery toward core damage. This analysis examines how a 40-year-old containment design, inadequate external event protection, and institutional overconfidence in probabilistic risk assessment created the conditions for multiple reactor meltdowns. On March 11, 2011, at 1446 JST, 3 boiling water reactors at Fukushima Daiichi Nuclear Power Plant responded exactly as their safety systems were designed. Control rods inserted automatically. Emergency diesels started on cue. Cooling pumps maintained circulation. For 41 minutes, the defense in-depth philosophy functioned precisely as nuclear engineers had envisioned for 4 decades. At 1527, seawater reached elevations that invalidated every assumption about external flooding. The plant's electrical systems, positioned at grade level in a country with documented tsunami history, lost power simultaneously across multiple units. Emergency procedures directed operators toward actions that were physically correct but practically impossible. Cooling systems that required power that no longer existed, isolation valves that could not be operated manually, and instrumentation that provided data about conditions that no longer mattered. The accident sequence that followed revealed a fundamental contradiction in reactor safety philosophy. Defense in depth had been designed as independent, redundant barriers against core damage. Yet under station blackout conditions, these defenses became sequential dependencies, each barrier requiring the previous one to function. The Mark Y containment designs, approved in the early 1970s, assumed that external power or diesel generators would always be available. The probabilistic risk assessments supporting continued operation calculated station blackout frequencies as acceptably low. The regulatory framework trusted that operator actions could compensate for design inadequacies. Multiple reactor meltdowns occurred not despite the safety systems, but because the safety systems had been designed for a different accident entirely. How can engineered safeguards guarantee failure when the conditions they were designed to prevent turn out to be the conditions they encounter? 1446 JST. On March 11, 2011, the Fukushima Daiichi Nuclear Power Plant responded to a magnitude 9 earthquake exactly as its designers intended. 3 boiling water reactors automatically inserted control rods within seconds. External power lines failed as anticipated. Emergency diesel generators started on schedule. Primary cooling systems maintained circulation. For 41 minutes, the defense in-depth philosophy that had governed nuclear safety for 4 decades functioned precisely as nuclear engineers had envisioned. The Mark I boiling water reactor containment design, conceived in the late 1960s and implemented at Fukushima Daiichi Units 1, 2, and 3, embodied the nuclear industry's fundamental safety philosophy. Multiple independent barriers between radioactive materials and the environment. The reactor pressure vessel formed the primary boundary. The steel and concrete primary containment provided secondary protection. The reactor building offered tertiary defense. Each barrier was designed to function independently, capable of preventing radioactive release even if other barriers failed. This independence assumption permeated every aspect of plant design and operation. Emergency core cooling systems included multiple trains of equipment, high-pressure coolant injection, reactor core isolation cooling, low-pressure coolant injection, and residual heat removal systems. Each system drew power from different electrical buses. Each had independent water sources. Each could theoretically maintain core cooling alone. The probabilistic risk assessments that supported plant licensing calculated the simultaneous failure of multiple independent systems as acceptably remote, less than one occurrence per million reactor years of operation. The electrical power design reflected this independence philosophy. Off-site power provided normal electrical supply through multiple transmission lines. On-site emergency diesel generators provided backup power if external sources failed. Station batteries supplied direct current for essential instrumentation and controls. Each power source was analyzed as an independent barrier against electrical failure. The combination of multiple power sources, according to design calculations, made prolonged station blackout, the simultaneous loss of all alternating current power, a beyond-design basis event with frequency low enough to exclude from safety analysis. Emergency procedures reinforced operator confidence in system independence. The emergency operating procedures developed for boiling water reactors assumed that at least one emergency cooling system would remain available, that at least one power source would function, and that instrumentation would provide reliable indication of plant conditions. Training scenarios focused on single system failures, single unit events, and recovery using available backup systems. The mental model embedded in procedures and training was clear. Defense in depth meant that something would always work. The instrument and control systems at Fukushima Daiichi relied on this same independence assumption. Reactor water level indication, the primary measure of core cooling adequacy, used multiple instruments measuring differential pressure across the reactor vessel. These instruments required both alternating current power for electronics and direct current power for operation. Temperature and pressure measurements throughout primary and secondary systems provided additional confirmation of cooling system performance. The instrumentation design assumed that electrical power would remain available to provide operators with accurate, timely information about plant conditions. Critical to understanding the subsequent failure sequence is recognizing that these design assumptions were not arbitrary. They reflected genuine engineering analysis based on available technology, historical operating experience, and regulatory requirements as they existed in the 1960s and early 1970s. The General Electric Mark I containment design had operated successfully for decades. Station blackout events had been rare and brief. External events severe enough to disable multiple independent systems simultaneously appeared to lie beyond credible accident scenarios. Yet, embedded within these reasonable assumptions lay vulnerabilities that would prove fatal under conditions that exceeded the design basis. The emergency diesel generators, positioned at grade level near the reactor buildings, shared common vulnerability to flooding despite their electrical independence. The ultimate heat sink, the seawater cooling system that removed heat from all safety systems, represented a single point of failure for all cooling trains despite their apparent redundancy. The instrumentation systems, while multiply redundant, all depended on the same physical principles and shared common vulnerabilities to environmental conditions beyond their design limits. The external event design basis for Fukushima Daiichi reflected the engineering consensus of its construction era. Seismic design considered the largest earthquakes in recorded regional history. Tsunami protection addressed the highest waves documented in available records. The plant's elevation of approximately 10 meters above mean sea level and tsunami design basis of 5.7 meters appeared conservative given 20th-century historical data. This approach followed established nuclear industry practice, design for credible events based on available evidence, then add conservative margins. However, this design philosophy contained an implicit assumption that historical records adequately bounded future natural events. Geological evidence of larger tsunamis in prehistoric times, while available to researchers, had not been incorporated into nuclear plant design requirements. The 869 AD Jogan tsunami, which geological studies suggested reached similar or greater heights than the March 2011 event, lay outside the formal design basis even though scientific investigation of its traces had been ongoing since the 1990s. The regulatory framework that governed Fukushima Daiichi operation reinforced confidence in these design assumptions. Japan's Nuclear and Industrial Safety Agency had approved the plant design, licensed its operation, and conducted periodic safety reviews. International nuclear safety organizations, including the International Atomic Energy Agency, had evaluated Japanese nuclear safety practices and found them robust. The nuclear industry's probabilistic risk assessment methodology, accepted by regulators worldwide, calculated the likelihood of severe accidents as acceptably low. This regulatory confidence reflected a deeper assumption about the relationship between design basis and physical reality. The design basis was treated not merely as an engineering boundary, but as a practical limit on credible accident scenarios. Events beyond the design basis were characterized as so unlikely that detailed analysis and preparation were unnecessary. Emergency planning zones around nuclear plants extended only 8 to 10 kilometers, reflecting confidence that severe accidents were either impossible or would have limited consequences. The institutional structure surrounding Fukushima Daiichi further reinforced design basis confidence. Tokyo Electric Power Company, as plant owner and operator, had strong economic incentives to maintain plant availability and avoid costly modifications. The close relationship between TEPCO and its regulator, characterized by personnel exchanges and shared professional culture, created an environment where design basis adequacy was rarely questioned. Independent technical challenges to fundamental design assumptions were uncommon and typically dismissed as overly conservative. Training and operational procedures embedded these assumptions so deeply that they became invisible to plant operators. Emergency drills practiced responses to design basis events using available safety systems. Simulator training reinforced operator familiarity with procedures that assumed electrical power, cooling water, and instrumentation availability. The operational philosophy emphasized following procedures, trusting instruments, and relying on engineered safety systems. This approach had proven successful through decades of safe operation, further validating confidence in design assumptions. Yet the March 11, 2011 earthquake and tsunami would reveal that these assumptions contained a fundamental logical error. Independence of safety systems assumed independence of threats to safety systems. Multiple barriers assumed multiple different failure modes. Defense in depth assumed that depth provided protection against all credible challenges. The events of March 11 would demonstrate that external events could create common mode failures that defeated multiple barriers simultaneously, that beyond design basis did not mean impossible, and that the defense-in-depth philosophy could become defense-in-sequence when systems designed as independent barriers became sequential dependencies. At 1527 JST, when the first tsunami wave reached Fukushima Daiichi, 40 years of design assumptions would begin their collision with physical reality. The plant that had survived the design basis earthquake would face flooding that invalidated every assumption about electrical power independence, cooling system redundancy, and instrumentation reliability. The operators who had trained to trust their systems and follow their procedures would find themselves in a situation where their systems provided false information and their procedures assumed capabilities that no longer existed. The institutional failures that made the Fukushima disaster inevitable did not begin on March 11, 2011. They accumulated over decades through a systematic pattern of organizational blindness, regulatory capture, and the gradual normalization of safety compromises. The technical vulnerabilities identified in Chapter 1 existed not in isolation, but within a human and institutional context that prevented their recognition and correction, even when warning signs became unmistakable. Tokyo Electric Power Company's awareness of tsunami risks at Fukushima Daiichi can be traced through internal documents spanning more than a decade before the accident. In 1997, TEPCO was presented with research by seismologists Katsuhiko Ishibashi and Koji Minora, indicating that historical tsunami heights in the region exceeded the plant's design basis. A TEPCO representative's recorded response revealed the institutional mindset that would prove fatal. I understood what Ishibashi was saying, but if we engineered factoring in every possible worst-case scenario, nothing would get built. This response encapsulated a fundamental misunderstanding of risk management in nuclear technology. The statement conflated prudent engineering conservatism with engineering impossibility, suggesting that addressing credible natural hazards would make nuclear plants unbuildable. This perspective reflected an organizational culture that prioritized construction and operation over comprehensive safety analysis, treating design basis limits as economic constraints rather than physical protection boundaries. Following the devastating 2004 Indian Ocean tsunami, TEPCO initiated a more systematic evaluation of tsunami risks at its nuclear facilities. The internal study, completed in 2007, calculated a 10% probability of a tsunami exceeding 6 meters height within 50 years. The Fukushima Daiichi reactors were specifically identified as vulnerable in this assessment. Yet rather than triggering immediate protective modifications, this analysis was characterized internally as unrealistic and effectively shelved. Company officials later testified that they dismissed their own technical analysis because implementing protective measures would have been expensive and operationally disruptive. Even more revealing was TEPCO's 2008 internal study that explicitly predicted tsunami heights exceeding 10 meters at the Fukushima site, more than double the plant's protective elevation. This analysis, based on updated understanding of regional earthquake sources, provided specific numerical predictions that proved remarkably accurate when compared to the actual March 11, 2011 tsunami heights of 14 to 15 meters. The study was completed 3 years before the accident, providing adequate time for protective modifications. Instead, company executives chose to suppress the findings while commissioning additional studies that they hoped would reach more favorable conclusions. The decision to inform Japan's Nuclear and Industrial Safety Agency about the 10-meter tsunami prediction occurred only 4 days before the March 11 earthquake. Too late for any protective action, even if regulators had demanded immediate modifications. This timing was not coincidental. Internal communications revealed that TEPCO intended to present the tsunami analysis alongside proposed studies that would take years to complete, effectively postponing any requirement for plant modifications indefinitely. The regulatory notification served as legal protection for the company rather than genuine safety communication. The regulatory environment that enabled these institutional failures reflected deep structural problems within Japan's nuclear oversight system. The Nuclear and Industrial Safety Agency operated under the Ministry of Economy, Trade, and Industry, which was simultaneously responsible for promoting nuclear power development. This dual mandate created inherent conflicts of interest that systematically favored industry perspectives over independent safety analysis. NISA officials regularly accepted higher-paying positions with nuclear utilities after government service, while utility executives served on government advisory committees. This revolving-door relationship, known in Japanese as amakudari, ensured that regulatory perspectives remained aligned with industry preferences. The manifestation of regulatory capture was visible in NISA's response to known technical deficiencies at TEPCO facilities. Throughout the 2000s, TEPCO had been repeatedly cited for safety violations, maintenance deferrals, and data falsification. In 2002, the company admitted to falsifying inspection records to conceal crack damage in reactor components at multiple facilities, including Fukushima Daiichi Units 1, 2, and 3. Rather than imposing severe sanctions or demanding comprehensive safety reviews, NISA worked with TEPCO to develop modified inspection standards that allowed continued operation of compromised systems. The pattern of regulatory accommodation continued through subsequent safety violations. In 2006, TEPCO admitted to falsifying coolant temperature data. In 2007, an earthquake damaged the Kashiwazaki Kariwa nuclear plant more severely than TEPCO initially disclosed, revealing systematic underestimation of seismic risks. In each case, NISA's response followed the same pattern: accept company explanations, negotiate compliance schedules, and avoid actions that would significantly impact plant operations or company finances. This regulatory approach sent a clear message that safety violations carried minimal consequences as long as companies cooperated with face-saving administrative processes. The technical basis for this regulatory leniency reflected sophisticated misuse of probabilistic risk assessment methodology. NISA and TEPCO routinely cited calculated low probabilities of severe accidents to justify continued operation of systems with known deficiencies. These calculations systematically excluded human factors, institutional failures, and external events beyond the design basis. The mathematical precision of probabilistic risk assessment created an illusion of scientific objectivity that obscured fundamental gaps in the analysis. Particularly problematic was the treatment of external events in risk calculations. Earthquake and tsunami frequencies were estimated using historical data that regulators and utilities knew to be incomplete. Geological evidence of larger prehistoric events was acknowledged in academic literature but excluded from regulatory analysis as unverifiable or not representative of current seismic conditions. This approach allowed continued operation under demonstrably inadequate design standards while maintaining mathematical justification for regulatory decisions. The institutional culture surrounding these technical and regulatory failures was reinforced by international validation from nuclear industry organizations. The International Atomic Energy Agency conducted regulatory review missions to Japan in 2007 and 2008, concluding that NISA represented international best practices in nuclear safety oversight. These evaluations praised Japan's comprehensive national legal and governmental framework for nuclear safety, and noted that all important safety elements receive regular due attention by both the licensee and NISA. The IAEA's institutional mandate to promote nuclear power alongside safety oversight created the same conflicts of interest that plague domestic regulation, leading to systematically optimistic assessments that reinforced industry confidence while overlooking fundamental structural problems. Training and operational procedures at Fukushima Daiichi reflected these institutional biases through their emphasis on design-basis events and available safety systems. Emergency drills practiced responses to single-unit accidents with electrical power available. Simulator training reinforced operator familiarity with procedures that assumed functional instrumentation and operable safety systems. Multi-unit accident scenarios, station blackout conditions lasting more than a few hours, and beyond design-basis external events received minimal attention in operator preparation. This training philosophy created what human factors specialists recognize as expertise traps, situations where deep knowledge of normal operations becomes a liability during abnormal conditions. Fukushima operators were extensively trained to trust their instruments, follow established procedures, and rely on engineered safety systems. These skills, while valuable during design-basis events, would prove counterproductive when instruments provided false information, procedures assumed non-existent capabilities, and safety systems failed to function as designed. The maintenance practices at Fukushima Daiichi further exemplified institutional prioritization of operational efficiency over comprehensive safety margins. Emergency diesel generators received scheduled maintenance according to manufacturer recommendations, but opportunities for enhanced protection against external events were systematically deferred as too expensive or operationally disruptive. Seawater intake systems, critical to ultimate heat removal for all safety systems, were maintained to support normal operations, but not upgraded to handle extreme external conditions. Documentation from NISA regulatory inspections revealed a pattern of findings and corrective actions that address symptoms rather than underlying vulnerabilities. Inspectors noted maintenance deferrals, procedure inadequacies, and training deficiencies, but these observations were treated as isolated issues requiring administrative fixes rather than indicators of systemic problems. The regulatory focus on compliance with existing requirements prevented recognition that the requirements themselves were fundamentally inadequate. The economic context surrounding these institutional failures created powerful incentives for maintaining the status quo. Fukushima Daiichi represented billions of dollars in capital investment, generating substantial revenue for TEPCO. Major safety modifications would have required extended plant shutdowns, significant capital expenditures, and potential challenges to fundamental design assumptions affecting TEPCO's entire nuclear fleet. The company's financial condition, already stressed by deregulation of Japan's electricity market, provided strong motivation to avoid costs that did not directly support revenue generation. Regulatory officials faced parallel economic pressures through Japan's commitment to nuclear power as a foundation of energy policy. Acknowledging fundamental design inadequacies at Fukushima would have implied similar problems at other facilities, potentially requiring industry-wide modifications that would severely impact nuclear power economics. The political commitment to nuclear expansion made regulatory officials reluctant to raise questions that could undermine public confidence or industry viability. These institutional failures created what organizational theorists recognize as a high-reliability organization paradox. The nuclear industry's emphasis on safety created powerful pressures to demonstrate that existing systems were adequate, that risks were well understood, and that operations remained within acceptable bounds. Acknowledging fundamental uncertainties or design inadequacies conflicted with institutional needs to project competence and control. This dynamic systematically discouraged the kind of independent thinking and worst-case analysis that could have identified and addressed the vulnerabilities revealed on March 11. The result was an institutional echo chamber where industry, regulatory, and political perspectives reinforced each other's confidence while systematically excluding voices that questioned fundamental assumptions. Independent researchers who identified tsunami risks larger than the design basis were dismissed as overly conservative. International experts who suggested enhanced external event protection were thanked for their input while their recommendations were quietly ignored. The institutional consensus that Fukushima Daiichi was adequately protected became self-reinforcing as each organization relied on others' expertise to validate its own conclusions. When NISA approved the lifetime extension for Fukushima Daiichi Unit 1 in February 2011, just weeks before the accident, the decision reflected 40 years of accumulated institutional failures. The regulatory analysis that supported continued operation acknowledged known uncertainties about seismic and tsunami risks while concluding that existing protective measures remained adequate. This conclusion was possible only because the regulatory process systematically excluded inconvenient evidence, relied on industry-favorable risk calculations, and prioritized administrative consistency over comprehensive safety analysis. The institutional conditions that made the Fukushima disaster inevitable were therefore not technical oversights or isolated regulatory failures, but systematic organizational dysfunction that prevented recognition and correction of known vulnerabilities. The human factors traps that would constrain operator response during the accident were embedded in training, procedures, and organizational culture that prioritized confidence in existing systems over preparation for conditions beyond the design basis. At precisely 14:46:23 JST, on March 11, 2011, the Pacific seafloor 130 kilometers east of Honshu ruptured along a fault zone, extending nearly 500 kilometers north to south. The magnitude 9 Tohoku earthquake released energy equivalent to 600 million times the Hiroshima atomic bomb, making it the most powerful earthquake ever recorded in Japan and among the 5 strongest worldwide since modern seismological monitoring began. At Fukushima Daiichi nuclear power plant, seismic monitoring instruments recorded ground acceleration, reaching 0.5, 2 grams in the north-south direction, 0.56 grams east-west, and 0.31 grams vertically. Severe ground motion but within the design parameters for critical plant structures. The reactor protection systems responded exactly as designed. Within seconds of detecting seismic acceleration exceeding preset limits, control rods inserted automatically into all 3 operating reactors through spring-loaded mechanisms that required no electrical power. Nuclear fission ceased immediately, though decay heat from radioactive fission products would continue generating approximately 7% of full power initially, declining gradually over days and weeks. This decay heat removal requirement, the fundamental challenge for reactor safety during shutdown conditions, would drive all subsequent events at Fukushima Daiichi. External electrical power to the plant was severed within minutes as transmission towers and lines throughout the region collapsed or were damaged by ground motion. This loss of off-site power, while serious, represented a design basis event for which Fukushima Daiichi was prepared. 13 emergency diesel generators started automatically across the 6-unit site, providing electrical power to safety systems, instrumentation, and cooling equipment. Primary cooling pumps continued operating, maintaining forced circulation through reactor cores. Control room operators monitored normal post-scram parameters as reactor pressure, temperature, and water level responded to automatic control system actions. For 41 minutes after the earthquake, Fukushima Daiichi demonstrated the effectiveness of defense in-depth engineering. Despite experiencing ground motion at the upper bounds of the design basis, safety systems functioned as intended. Reactor buildings, designed to withstand seismic forces, maintained structural integrity. The primary containment vessels showed no signs of damage. Emergency cooling systems operated normally. Control room instrumentation provided operators with clear, consistent information about plant status. The initial earthquake, despite its unprecedented magnitude, had been successfully managed through engineered safety systems and automatic protective actions. Plant operators followed post-scram procedures that had been validated through decades of training and operational experience. These procedures assumed continued availability of electrical power, either from off-site sources or emergency diesels, and reliable operation of primary cooling systems. The operators had no reason to suspect that their normal post-earthquake response was inadequate, or that their instrumentation might soon become unreliable. Their training and experience confirmed that following established procedures while monitoring key parameters would ensure safe plant conditions. At 1527 JST, seismic waves traveling at approximately 7 kilometers per second across the Pacific Ocean floor reached the Japanese coast as tsunami waves moving at 700 kilometers per hour in deep water. The first wave approached Fukushima Daiichi at approximately 1527, followed by larger waves at 1535 and 1537. Wave heights measured between 14 and 15 meters at the plant site, nearly 3 times the design basis tsunami height of 5.7 meters and 4 to 5 meters higher than the plant's protective elevation of approximately 10 meters above sea level. The physical progression of tsunami flooding at Fukushima Daiichi followed predictable fluid dynamics principles, but its consequences reflected the fundamental inadequacy of plant design for external flooding protection. Seawater overtopped the plant's seawalls and spread across the site, following topographical gradients toward lower elevations. The emergency diesel generator buildings, designed to protect equipment from seismic forces but not from flooding, were inundated with seawater that penetrated through doors, ventilation openings, and cable penetrations. Within minutes, 12 of the 13 emergency diesel generators at Fukushima Daiichi lost function due to seawater damage to electrical components, fuel systems, or cooling systems. Only the air-cooled emergency diesel for Unit 6, positioned at higher elevation, continued operating. This loss of emergency AC power was compounded by flooding of electrical switchgear rooms, battery rooms, and seawater intake structures that provided ultimate heat removal for all safety systems. The plant had transitioned from a design basis station blackout, expected to last hours with available coping systems, to an extended station blackout with no reliable means of core cooling. The implications of this transition were not immediately apparent to control room operators. Battery-powered instrumentation continued providing readings that appeared normal or explicable within familiar operational parameters. Direct current power supplies, while depleted by emergency loads, maintained function for several hours. Communication systems allowed coordination between control rooms and with off-site emergency response organizations. The dramatic nature of the external event was obvious, but the specific consequences for nuclear safety systems would become clear only gradually as operators attempted to implement emergency procedures designed for very different circumstances. Reactor physics during the initial hours following tsunami impact followed predictable principles, but operators lacked the instrumentation and analysis capabilities to fully understand the progression. With AC power lost, primary cooling pumps stopped operating, ending forced circulation through reactor cores. Natural circulation flow, driven by thermal convection, provided limited cooling capability but required intact primary system geometry and adequate driving pressure differences. As reactor coolant heated and began forming steam, relief valves opened automatically to prevent pressure vessel damage, but each relief valve operation vented reactor coolant inventory that could not be replaced without functioning injection systems. The reactor core isolation cooling and high-pressure coolant injection systems, designed to operate during station blackout conditions, functioned initially on battery power and steam pressure. These systems could maintain core cooling for several hours, but their operation depended on adequate electrical power for controls, adequate steam pressure for turbine-driven pumps, and adequate water inventory in suppression pools that served as heat sinks. As station blackout continued, each of these dependencies would be progressively challenged. Unit 1 experienced the most rapid progression toward core damage due to its smaller suppression pool volume and older isolation cooling system design. The reactor core isolation cooling system operated for approximately 1 hour after the tsunami before losing function, possibly due to steam binding or loss of adequate suction head. Without makeup water injection, reactor water level began decreasing as continued relief valve operation depleted coolant inventory. Operators, working with battery-powered instruments and emergency lighting, attempted to restart cooling systems and establish alternative water sources, but their efforts were constrained by flooding damage to essential equipment and electrical systems. Unit 2 and Unit 3 reactor core isolation cooling systems operated longer due to larger suppression pool volumes and different system configurations, but similar physics governed their progression toward core uncovery. Steam-driven pumps maintained injection capability, while steam pressure remained adequate, but suppression pool temperatures increased as systems dumped heat into finite water inventories. Rising suppression pool temperatures eventually degraded pump suction conditions and reduced available net positive suction head below system requirements. The instrument and control systems that operators depended on for understanding plant conditions began providing misleading information as environmental conditions exceeded design parameters. Reactor water level indication, based on differential pressure measurements between reactor vessel locations, assumed specific fluid densities and hydrostatic head relationships that became invalid as high-temperature steam displaced water in reference legs. These instruments continued, displaying readings, but the readings no longer accurately represented actual water levels above reactor fuel. Similarly, containment pressure and temperature instruments provided data, but operators had limited ability to interpret readings outside normal operational ranges. Suppression pool temperatures exceeding 100 degrees Celsius indicated loss of heat removal capability, but specific heat loads and projection of future conditions required engineering calculations that were impossible without computational tools and reference materials that had become inaccessible due to flooding and power loss. The emergency operating procedures available to operators had been developed for design basis events with key assumptions about available equipment and plant conditions. These procedures assumed electrical power for equipment operation and instrument reliability, availability of multiple cooling water sources, and ability to operate valves and pumps through normal control systems. As these assumptions proved invalid, operators found themselves implementing procedures that required capabilities they no longer possessed. Communication with off-site technical support was maintained through battery-powered systems, but technical experts located at TEPCO headquarters and government facilities lacked direct access to plant instrumentation and had to rely on periodic reports from control room operators. This communication limitation prevented real-time engineering analysis of plant conditions and restricted technical support to general guidance rather than specific procedural direction based on actual plant parameters. The progression from design basis accident to beyond design basis emergency was not marked by dramatic failures or obvious indication changes. Instead, it represented a gradual degradation of system capability and instrument reliability that left operators increasingly uncertain about plant conditions and appropriate response actions. Equipment that appeared functional might actually be damaged. Instruments that displayed reasonable values might be providing false information. Procedures that had proven effective during training scenarios might be inadequate for actual plant conditions. By late afternoon on March 11th, control room operators recognized that they faced conditions outside normal emergency procedures, but lacked clear guidance for response actions under extended station blackout, with compromised cooling systems. Technical specifications required core cooling under all conditions, but the engineered systems designed to provide cooling were no longer functional. Alternative cooling methods would require improvisation using equipment and water sources that had not been analyzed for nuclear safety applications. The decision points facing operators were constrained by incomplete information about actual plant conditions, limited options for system restoration, and uncertainty about the effectiveness of potential response actions. Each hour of delay increased the likelihood of core damage, but hasty actions using inappropriate equipment could worsen conditions or create new safety hazards. The operators found themselves in the position of managing a nuclear emergency using industrial fire protection equipment, uncertain whether their actions would prove beneficial or harmful. The physics of core heat-up and potential damage were well understood in principle, but specific timing and progression depended on numerous variables that operators could not accurately determine with available instrumentation. Core uncovery would begin when reactor water level dropped below the top of active fuel assemblies. Steam cooling would provide limited heat removal until cladding temperatures reached approximately 1,200 degrees Celsius, when zirconium steam reactions would begin generating additional heat and hydrogen gas. Continued temperature rise would eventually cause fuel cladding failure, fission product release, and potential fuel melting. These physical processes were irreversible once initiated, making time to core damage the critical parameter for emergency response effectiveness. However, calculating this timing required knowledge of actual water level, decay heat generation rates, system leakage rates, and heat removal capabilities, information that was either unavailable or unreliable given instrumentation limitations and environmental conditions beyond design parameters. As evening approached on March 11, 2011, the gap between operator understanding and physical reality continued widening. Plant conditions were deteriorating according to predictable engineering principles, but the specific timing and magnitude of deterioration remained uncertain. Emergency response actions were being implemented based on incomplete information about their necessity and effectiveness. The fundamental assumption underlying all nuclear emergency procedures, that operators would have sufficient reliable information to guide appropriate response actions, had been invalidated by conditions that exceeded both design basis assumptions and procedural guidance. The transition from recoverable emergency to irreversible core damage at Fukushima Daiichi occurred through a cascade of physical processes that operators could not directly observe, could not accurately measure, and ultimately could not prevent with available equipment. The failure chain that began with external flooding progressed according to fundamental reactor physics and thermal hydraulics principles, but the specific timing and magnitude of each step remained hidden behind instrumentation that provided technically accurate but physically misleading information. Reactor water level indication represents the most critical example of how instrument design assumptions failed under beyond design basis conditions. The Foxborough differential pressure transmitters used throughout the Fukushima units measured pressure differences between the reactor vessel bottom and a reference leg connected to the reactor vessel at the level of the main steam lines. Under normal conditions, this arrangement accurately calculated water level by comparing hydrostatic pressure differences corresponding to water column height. The instruments themselves functioned correctly throughout the accident sequence, but the physical assumptions underlying their measurements became invalid as plant conditions exceeded design parameters. The fundamental problem was reference leg flashing, a phenomenon where heated water in the instrument reference lines converted to steam, reducing the hydrostatic pressure used for level calculation. As reactor cooling degraded and suppression pool temperatures rose, instrument reference legs heated beyond 100 degrees Celsius, causing water to vaporize and creating false low-pressure readings. The differential pressure instruments interpreted this condition as higher reactor water level than actually existed. Operators, trained to trust their instruments and lacking alternative level measurement methods, continued believing they maintained adequate core cooling even as fuel assemblies were becoming uncovered. This instrumentation failure was not a malfunction in the conventional sense. The differential pressure transmitters operated within their design specifications and provided mathematically correct calculations based on measured pressure differences. The failure lay in the invalid assumptions about fluid conditions within the reference legs under severe accident conditions, No alarm indicated instrument unreliability. No backup measurement confirmed or contradicted the primary indication. The control room displays showed water level readings that appeared reasonable and consistent with other available information. Unit 1 experienced the earliest and most severe core damage progression due to rapid loss of injection capability and smaller coolant inventory. The reactor core isolation cooling system lost function approximately 1 hour after the tsunami, leaving the reactor vessel isolated with no makeup water source. Natural circulation provided limited cooling as long as adequate water inventory remained above the fuel assemblies, but continued operation of relief valves to maintain pressure control steadily depleted this inventory. The physics of core uncovery in Unit 1 followed predictable stages that operators could not directly monitor. As water level dropped below the top of active fuel assemblies around 18 on March 11, the uppermost portions of fuel rods began experiencing steam cooling rather than water submersion. Steam cooling provides significantly lower heat transfer coefficients than liquid water cooling, causing fuel cladding temperatures to rise rapidly. Zircaloy fuel cladding maintains structural integrity and fission product retention up to approximately 1,200 degrees Celsius, beyond which oxidation reactions with steam begin generating additional heat and hydrogen gas. The zirconium steam reaction that initiated in Unit 1 during the evening of March 11 represented a critical threshold in the accident progression. This exothermic chemical reaction, zirconium plus steam producing zirconium oxide plus hydrogen, added significant heat generation beyond decay heat alone, accelerating the temperature rise of already overheated fuel. Hydrogen production from this reaction would later create explosion hazards throughout the reactor building, but the immediate consequence was loss of cladding integrity and beginning of fission product release from the fuel matrix. Temperature calculations based on estimated timing of core uncovery suggest that fuel cladding in Unit 1 reached 1,200 degrees Celsius sometime during the night of March 11 to 12. Beyond this temperature, the combination of decay heat, zirconium oxidation heat, and reduced heat removal capability drove fuel temperatures toward the melting point of zirconium oxide, at approximately 2,800 degrees Celsius. Once this threshold was exceeded, fuel geometry began changing as cladding materials relocated and fuel pellets began sintering together, fundamentally altering core heat transfer characteristics and making recovery of normal cooling geometry impossible. The progression toward fuel melting in Unit 1 was essentially irreversible once initiated, but operators lacked any direct indication of these processes. Containment radiation monitors provided some evidence of fission product release, but specific core damage assessment required interpretation of multiple indirect indicators that were difficult to evaluate under emergency conditions. Temperature instruments within the reactor vessel had limited range and accuracy under severe accident conditions. Hydrogen concentration measurements were not available in the reactor building atmosphere. Unit 2 and Unit 3 followed similar physical progressions but with different timing due to longer operation of their reactor core isolation cooling systems. Unit 3 feed system operated until the morning of March 12, providing approximately 13 hours of core cooling after the tsunami. Unit 2 feed system continued functioning until March 14, giving operators more time to establish alternative cooling methods but ultimately following the same path toward core damage when injection capability was finally lost. The reactor core isolation cooling and high-pressure coolant injection systems demonstrated both the strengths and limitations of engineered safety systems under beyond design basis conditions. These steam-driven systems required no external electrical power and could operate for extended periods using reactor steam pressure and suppression pool water inventory. However, their continued operation depended on maintaining adequate steam pressure, adequate suppression pool cooling, and adequate net positive suction head for pump operation. As station blackout continued and suppression pool temperatures rose due to continued heat input without heat removal, the operating environment for these systems gradually degraded beyond design parameters. Steam binding occurred when suppression pool temperatures approached saturation, reducing available net positive suction head below system requirements. Cavitation and flow instabilities developed as systems attempted to operate outside their design envelope. Eventually, these systems lost function not through mechanical failure but through invalidation of their operating assumptions. The loss of ultimate heat sink, the seawater cooling systems that provided the final heat removal path for all reactor safety systems, represented the fundamental cause of the failure progression at all three units. Nuclear reactors require continuous heat removal even after shutdown due to ongoing decay heat generation. During normal operations, this heat removal occurs through the main condenser and circulating water systems. During emergency conditions, safety systems transfer heat to suppression pools, service water systems, or other intermediate heat sinks that must ultimately reject heat to the environment. At Fukushima Daiichi, seawater intake structures and circulating water pumps were damaged by tsunami flooding, eliminating the plant's ultimate heat sink capability. This meant that any heat added to plant systems, whether from decay heat, pump operation, or zirconium oxidation, could not be removed from the site. Suppression pools, designed as intermediate heat sinks for short-term emergency conditions, gradually heated towards saturation as they absorbed heat with no removal capability. Once suppression pool temperatures reached saturation, continued heat addition would cause boiling and steam formation, eventually leading to containment overpressure if not relieved. The containment response at each unit reflected the interaction between rising internal heat loads and finite containment volumes. Primary containment systems at Fukushima Daiichi used Mark I pressure suppression designs with relatively small volumes compared to other containment types. These designs effectively managed steam and pressure loads during design basis accidents, but their limited volume made them vulnerable to overpressure during extended events with continued heat addition and no heat removal. As core damage progressed in each unit, fission products released from damaged fuel added to containment atmosphere contamination and heat loads. Noble gases and volatile fission products like iodine and cesium were released first as fuel cladding failed. Later fission product releases occurred as fuel temperatures reached levels causing fuel pellet degradation and volatile species vaporization. These releases increased containment pressure and radiation levels while providing operators with indirect evidence of core damage severity. The decision to vent primary containment systems, releasing radioactive materials to the environment to prevent containment structural failure, represented a fundamental compromise of defense-in-depth principles. Containment venting was a recognized severe accident management strategy, but its implementation at Fukushima required manual operation of valves that were designed for remote operation under normal plant conditions. Operators wearing emergency protective equipment worked in high radiation areas to manually open valves, accepting significant personal radiation exposure to prevent containment failure that could release even larger quantities of radioactive materials. The hydrogen explosions that destroyed reactor building superstructures at Units 1, 3, and 4 resulted from hydrogen gas accumulation beyond flammable concentration limits. Hydrogen produced by zirconium steam reactions within damaged reactor cores was transported through containment venting systems into reactor building atmospheres. These buildings were not designed as pressure-retaining structures and had no provisions for hydrogen concentration control or ignition prevention. When hydrogen concentrations reached approximately 4% in air, explosive combustion occurred, destroying building roofs and walls while leaving primary containment structures largely intact. The Unit 4 explosion was particularly revealing about systemic design vulnerabilities. Unit 4 had been shut down for refueling before March 11 and should not have generated hydrogen from core damage. However, Unit 4's reactor building was destroyed by hydrogen explosion on March 15, indicating that hydrogen had migrated from Unit 3 through shared ventilation systems or other pathways. This demonstrated that multi-unit accidents could create failure modes that had not been considered in single-unit safety analyses. The timing and severity of hydrogen explosions provided operators and emergency response personnel with dramatic evidence of core damage severity. But this information came too late to prevent fuel damage and came with the additional hazard of structural damage that complicated access for emergency response equipment. The explosions also created debris and contamination that hampered subsequent recovery efforts, while providing unmistakable evidence to the public that the accident had progressed far beyond design basis conditions. Throughout the core damage progression at all three units, operators attempted to establish alternative cooling using whatever equipment remained available. Fire engines and concrete pump trucks were positioned to inject seawater through jury-rigged connections to safety system piping. These efforts represented heroic improvisation under extremely hazardous conditions, but their effectiveness was limited by uncertainty about core geometry, unknown effectiveness of injection into damaged fuel configurations, and potential adverse effects of seawater injection on nuclear fuel and primary system materials. The decision to inject seawater into reactor systems, unprecedented in commercial nuclear power history, reflected the recognition that preservation of equipment was secondary to prevention of further radiological releases. Seawater injection would cause massive corrosion damage to primary systems, essentially ensuring that the reactors could never return to service, but offered the possibility of establishing some cooling capability for damaged fuel masses. The long-term effectiveness of seawater cooling depended on factors that could not be determined during the emergency: the extent of fuel damage, the configuration of relocated fuel debris, and the ability to establish adequate heat removal through damaged systems. The physical evidence that later emerged from detailed inspections confirmed the fundamental accuracy of core damage assessments based on hydrogen production, containment radiation levels, and other indirect indicators. Reactor vessel examinations revealed extensive fuel damage with significant fuel debris relocation. Containment inspections found evidence of corium formation and migration outside the original core configuration. Suppression pool examinations revealed structural damage from high-temperature conditions and hydrogen combustion effects. This post-accident evidence validated theoretical understanding of severe accident progression, while revealing that actual conditions had been even more severe than real-time assessments suggested. The core damage at Fukushima Daiichi was not merely fuel cladding failure or partial fuel melting, but extensive fuel relocation and corium formation that challenged fundamental assumptions about core geometry and coolability. Recovery efforts were therefore directed at cooling unknown configurations of fuel debris, rather than restoring normal cooling to intact fuel assemblies. The recognition that conventional safety systems had failed to prevent core damage at Fukushima Daiichi forced operators and emergency response personnel into uncharted territory where established nuclear procedures provided no guidance. Beginning on the morning of March 12th, emergency response efforts shifted from following standard operating procedures to implementing unprecedented measures using equipment never intended for nuclear applications. These stabilization attempts, while heroic in execution, introduced new uncertainties and risks while operating under severe constraints that made success difficult to achieve or verify. The decision to inject seawater into reactor pressure vessels represented the most significant departure from established nuclear practice in commercial reactor history. No commercial nuclear plant had ever deliberately injected seawater into reactor systems due to the severe corrosion and contamination effects of salt on nuclear fuel, control systems, and primary circuit materials. The chloride content in seawater causes rapid corrosion of zirconium fuel cladding and stainless steel components, while sodium content creates activation products and long-term contamination issues. These concerns were set aside at Fukushima because the alternative, continued core damage with potential containment failure, posed greater risks to public safety. The technical implementation of seawater injection required improvisation using fire protection equipment and industrial pumping systems never analyzed for nuclear safety applications. Tokyo Fire Department pumper trucks and concrete pumping vehicles were positioned to inject through fire protection system connections that provided access to safety system piping. These connections were designed for building fire suppression, not reactor vessel injection, creating uncertainties about flow rates, pressure capabilities, and system compatibility under emergency conditions. The effectiveness of seawater injection into damaged reactor cores involved complex thermal hydraulic phenomena that could not be accurately analyzed without detailed knowledge of fuel debris configuration. If fuel assemblies maintained relatively intact geometry, seawater cooling could provide adequate heat removal to stabilize temperatures below further damage thresholds. However, If significant fuel relocation had occurred, injected water might not contact relocated fuel debris effectively, or might create steam that could not be adequately vented from the reactor vessel. Without direct visual access to core conditions, operators could only infer effectiveness through indirect measurements of injection flow rates, reactor pressure responses, and containment radiation levels. Unit 1 seawater injection began at approximately 2020 on March 12, roughly 30 hours after tsunami impact and several hours after the hydrogen explosion that destroyed the reactor building superstructure. The delay in establishing injection reflected both the time required to position equipment and the operational challenges of working in high radiation environments with limited electrical power and communications. Fire department personnel and TEPCO workers wearing full protective equipment laid hoses across debris-covered terrain while monitoring radiation exposure rates that frequently exceeded normal occupational limits. The injection strategy for Unit 1 faced immediate technical challenges related to reactor vessel pressure and injection system capabilities. Reactor pressure had to be reduced below fire pump discharge pressure to establish flow, requiring successful operation of relief valves that might have been damaged by high-temperature conditions or contaminated with salt deposits from previous injection attempts. Pressure control during injection required careful coordination between relief valve operation and injection flow rates to maintain adequate vessel inventory without causing overpressure. Unit 3 seawater injection commenced on March 13 following similar equipment positioning and pressure reduction procedures, but with the added complexity of concurrent hydrogen buildup that would lead to explosive combustion on March 14. The Unit 3 explosion occurred while seawater injection was in progress, creating additional hazards for emergency response personnel and potentially damaging injection equipment. The explosion demonstrated that stabilization efforts were proceeding while fundamental containment and building integrity remained at risk from ongoing hydrogen generation and accumulation. The Unit 2 experience revealed additional complexities in severe accident management as systems that had operated longer began failing in unexpected ways. Unit 2's reactor core isolation cooling system continued operating until March 14, providing operators with hope that core damage might be less severe than in Units 1 and 3. However, when the system finally failed, rapid pressure and temperature increases indicated that core damage had been occurring despite continued injection, suggesting that system flow rates had been inadequate for heat removal requirements or that injection had not been reaching the core effectively. Containment venting operations, implemented to prevent containment overpressure failure, required manual valve operations in extremely high radiation environments. The containment venting system was designed for remote operation from the control room under normal plant conditions, but station blackout had disabled remote operation capabilities. Operators wearing emergency protective equipment worked to manually open isolation valves while exposed to radiation fields that exceeded emergency exposure guidelines established for nuclear workers. The venting process itself introduced new technical challenges related to fission product release pathways and hydrogen management. Containment venting released radioactive materials to the atmosphere through pathways that bypassed normal filtration systems, creating off-site contamination that complicated evacuation planning and emergency response coordination. Additionally, venting directed hydrogen-laden gas into reactor-building atmospheres that lacked hydrogen control systems, contributing to the explosive conditions that destroyed building superstructures. The coordination of venting operations with seawater injection attempts created operational conflicts that had never been analyzed in emergency procedures. Venting reduced containment pressure to prevent structural failure, but also reduced back pressure that helped drive injection flow into reactor vessels. Injection flow rates varied with system pressure relationships that changed as venting operations proceeded, making it difficult to maintain consistent cooling flow to damaged cores. These interactions between emergency response actions had not been considered in emergency procedure development because simultaneous severe core damage and containment challenge had been considered beyond credible accident scenarios. Unit 4 presented unique challenges that revealed additional systemic vulnerabilities in multi-unit accident response. Unit 4 had been shut down for refueling when the earthquake occurred, with its full reactor core discharged to the spent fuel storage pool located in the reactor building. The spent fuel pool contained not only the recently discharged core, but also several previous reactor cores stored underwater pending transfer to longer-term storage facilities. This inventory represented significantly more radioactive material than a single reactor core and generated substantial decay heat that required continuous cooling. The spent fuel pool cooling systems at Unit 4 were lost with the station blackout, but initial assessments suggested that the large water inventory in the pool would provide adequate cooling for several days without makeup. However, the March 15 hydrogen explosion at Unit 4 indicated that hydrogen had been generated within the spent fuel pool, suggesting that water levels had dropped sufficiently to uncover stored fuel assemblies. The source of this hydrogen was initially uncertain. It could have resulted from fuel uncovery in the spent fuel pool, or it could have migrated from Unit 3 through shared ventilation or other pathways. The possibility of spent fuel pool uncovery created new urgency for emergency response because spent fuel pools lacked the containment barriers present around reactor cores. If stored fuel assemblies became uncovered and overheated, radioactive releases could occur directly to the atmosphere without containment protection. The spent fuel pool inventory represented a larger total radioactive source term than individual reactor cores, making uncontrolled spent fuel pool heating potentially more serious than reactor core damage. Attempts to restore spent fuel pool cooling involved helicopter water drops and high-pressure water spraying from ground-based equipment. These operations were conducted while reactor buildings remained structurally compromised from previous explosions and while radiation levels in the area remained extremely high. The effectiveness of external water addition to spent fuel pools was uncertain because pools were located inside damaged buildings, where direct visual confirmation was impossible, and where alternative drainage pathways might prevent water level restoration. The multi-unit nature of the Fukushima accident created coordination challenges that exceeded the scope of existing emergency procedures and organizational structures. Simultaneous emergencies at 3 reactor units and 1 spent fuel pool required resources and expertise that no single nuclear facility was designed to provide. Equipment, personnel, and technical support had to be allocated among competing priorities while working under severe time pressure and hazardous conditions that limited detailed planning and analysis. Communication and decision-making during stabilization efforts were complicated by the loss of normal plant instrumentation and communication systems. Key decisions about injection strategies, venting timing, and resource allocation had to be made based on limited information from field observations, periodic instrumentation readings, and engineering estimates that could not be verified under existing conditions. The normal processes for technical review and approval of unusual operations were condensed or bypassed, entirely due to emergency conditions. The psychological and organizational stress of managing multiple simultaneous severe accidents created additional human factors challenges that had not been considered in emergency procedure development. Control room operators, emergency response personnel, and technical support staff were working extended shifts under extreme stress while personally concerned about family members affected by the broader earthquake and tsunami disaster. Normal shift changes, technical briefings, and decision review processes were disrupted by the scope and duration of the emergency. Radiation protection during stabilization efforts required constant balancing between emergency response objectives and worker safety. Radiation exposure rates throughout the plant site frequently exceeded normal occupational limits, forcing rotation of personnel and limitation of work time in critical areas. Emergency exposure guidelines allowed higher doses for life-saving operations, but implementing these guidelines required case-by-case decisions about which activities justified increased worker exposure. The improvised nature of stabilization equipment created additional uncertainties about system reliability and effectiveness. Fire trucks and concrete pumpers were operated continuously for days under conditions far exceeding their normal duty cycles. Hose connections and electrical systems were exposed to salt spray, debris, and radiation that could cause unexpected failures. Equipment maintenance and repair had to be performed in contaminated areas using emergency procedures that prioritized immediate function over long-term reliability. By March 15th, emergency response efforts had established seawater injection to all 3 damaged reactor units and had implemented various measures to address spent fuel pool concerns. But fundamental uncertainties remained about the effectiveness of these measures and the stability of plant conditions. Reactor vessel water levels remained uncertain due to instrument reliability questions. Core damage extent could not be directly assessed. Containment integrity status was unclear. Spent fuel pool conditions remained unknown due to access limitations. The stabilization phase demonstrated both the capabilities and limitations of emergency response when facing beyond design basis conditions. Heroic efforts by plant operators, emergency responders, and support personnel had prevented immediate containment failures and established some degree of cooling for damaged cores. However, the long-term effectiveness of these measures remained uncertain, and new risks had been introduced through the use of improper equipment and procedures that had never been analyzed for nuclear applications. The plant remained in a precarious state where continued human intervention was required to prevent further deterioration, but where the success of intervention efforts could not be reliably verified. The true extent of core damage and system failure at Fukushima Daiichi would remain hidden for months after the initial accident sequence, concealed behind high radiation fields, structural damage, and the physical impossibility of direct inspection. The gap between real-time assessments during the emergency and actual plant conditions revealed by subsequent forensic investigation demonstrated how severely beyond design basis events could invalidate fundamental assumptions about accident progression, system behavior, and recovery effectiveness. This forensic evidence would ultimately reshape understanding of severe accident phenomena while exposing systemic failures in nuclear safety assessment that extended far beyond the specific technical problems at Fukushima. The first definitive evidence of actual core damage severity came from robotic inspections conducted months after the accident, when radiation levels had decreased sufficiently to permit remote examination of reactor vessel and containment interiors. These inspections revealed fuel damage far more extensive than initial assessments had suggested. In Unit 1, underwater camera examinations showed no recognizable fuel assembly structure within the reactor vessel, indicating complete core melt and relocation of molten fuel debris to the vessel lower head. Similar examinations in Units 2 and 3 revealed varying degrees of fuel damage and debris relocation that confirmed the severity of core damage progression during the accident. The discovery of extensive fuel relocation provided crucial insights into the effectiveness of emergency cooling efforts during the accident. Seawater injection strategies had been based on assumptions that fuel assemblies maintained relatively intact geometry within the original core configuration. The forensic evidence showed that significant portions of fuel had relocated outside the active core region, meaning that injection flow patterns established for normal core geometry were ineffective for cooling relocated fuel debris. This explained why injection flow rates that appeared adequate based on engineering calculations had not prevented continued core damage progression. Containment examination results revealed structural damage patterns that contradicted pre-accident analyses of containment performance under severe accident conditions. The Mark I containment design was expected to maintain structural integrity even under significant overpressure conditions, providing the final barrier against large radioactive releases. However, forensic inspections found evidence of containment boundary failures that had allowed radioactive materials to escape primary containment and reach the environment through uncontrolled pathways. These failures included damaged electrical and piping penetrations, compromised containment isolation systems, and structural damage to containment components. The pattern of radioactive contamination found throughout the Fukushima site provided additional evidence of containment performance that deviated significantly from design expectations. Contamination surveys revealed radioactive materials in areas that should have remained uncontaminated if containment barriers had functioned as designed. High-activity contamination was found in reactor building areas outside primary containment, in turbine buildings connected to reactor buildings, and in outdoor areas that indicated atmospheric release pathways beyond those intended for containment venting operations. Atmospheric and oceanic radioactive release assessments refined through extensive environmental monitoring and computer modeling, revealed total release quantities that exceeded initial estimates and demonstrated the inadequacy of emergency planning assumptions. The total atmospheric release of cesium-137, a long-lived fission product that serves as a key indicator of accident severity, was calculated at approximately 15% of the total reactor core inventory, a release magnitude that placed the Fukushima accident at the highest level of the International Nuclear Event Scale alongside the Chernobyl accident. The oceanic releases, which continued for months after the initial accident sequence, demonstrated how containment failures could create ongoing contamination pathways that were not considered in accident consequence assessments. Contaminated water from cooling operations, groundwater infiltration, and storage tank leakage created persistent oceanic contamination that affected marine life and fishing operations across a broad area of the Pacific Ocean. These ongoing releases showed that severe accident consequences could extend far beyond the immediate emergency phase. Evacuation effectiveness assessments revealed systematic failures in emergency planning that paralleled the technical failures in plant design. The emergency planning zone around Fukushima Daiichi extended only 8 to 10 kilometers, based on consequence assessments that assumed effective containment of radioactive materials and limited environmental releases. The actual contamination patterns required evacuation zones extending up to 30 kilometers from the plant, with some highly contaminated areas identified at distances exceeding 50 kilometers. This demonstrated that emergency planning assumptions about accident consequences were as inadequate as design basis assumptions about accident prevention. The Special Purpose Individual Dosimetry, SPEEDY Atmospheric Dispersion Prediction System, developed specifically to guide emergency response decisions during nuclear accidents, provided another example of how sophisticated technical systems failed under actual emergency conditions. SPEEDY calculations required accurate source term estimates and meteorological data to predict contamination patterns, but both types of input data were unavailable or unreliable during the Fukushima emergency. Without reliable source terms, SPEEDY predictions were essentially meaningless for emergency planning. Yet these predictions were not released to the public for days after the accident, preventing individuals from making informed decisions about protective actions. The evacuation process itself revealed organizational failures that compounded technical system failures. Evacuation orders were issued in a series of expanding zones as the severity of contamination became apparent, creating confusion and potential additional exposure for evacuees who were relocated multiple times. Some evacuees were inadvertently moved to areas with higher contamination than their original locations due to lack of real-time contamination monitoring data. Hospital and nursing home evacuations resulted in numerous deaths among elderly patients who could not survive the stress of emergency relocation. Long-term contamination assessments provided the most sobering evidence of accident consequences that had been dismissed as incredible in pre-accident safety analyses. Large areas of agricultural land became unsuitable for food production due to cesium contamination that would persist for decades, due to the 30-year half-life of cesium-137. Entire communities were permanently displaced, with residents unable to return to homes and businesses contaminated beyond acceptable limits for normal occupancy. The economic impact of lost agricultural production, business displacement, and decontamination costs reached hundreds of billions of dollars, economic consequences that exceeded the total value of nuclear power generation in Japan. Decontamination efforts, while technically feasible for limited areas, demonstrated the practical limitations of environmental restoration following large-scale radioactive contamination. Soil removal and replacement could reduce contamination levels in residential and commercial areas, but generated enormous volumes of radioactive waste that required long-term storage in facilities that did not exist when decontamination began. Forest decontamination proved largely ineffective due to the continuous redistribution of contamination through natural processes. Agricultural decontamination required treatment of vast areas with uncertain long-term effectiveness. The institutional response to forensic evidence revealed how organizational factors that contributed to the accident continued to impede learning from accident consequences. Initial official assessments minimized accident severity and environmental impact, emphasizing that no one was killed by radiation while ignoring the broader health, economic, and social consequences of large-scale contamination. These assessments reflected the same institutional biases that had prevented recognition of accident vulnerabilities before March 11, 2011. International nuclear industry response to Fukushima evidence demonstrated how global institutional factors reinforced local biases against acknowledging fundamental safety assessment failures. While various technical modifications were implemented at nuclear plants worldwide following Fukushima, the fundamental probabilistic risk assessment methodology that had failed to identify Fukushima vulnerabilities remained largely unchanged. External event protection was enhanced, but the basic assumption that beyond design basis events could be excluded from safety analysis through low probability calculations was maintained. The regulatory response to Fukushima evidence in Japan and internationally revealed the persistence of institutional capture that had contributed to the original accident. New regulatory organizations were established with promises of independence from promotional activities, but staffed largely with personnel from the same technical community that had developed and defended pre-accident safety assessments. New safety requirements were implemented but based on the same risk assessment methodologies that had proven inadequate for identifying actual vulnerabilities. The most fundamental lesson from Fukushima forensic evidence was that defense in-depth safety philosophy, as implemented in nuclear power systems, contained logical contradictions that made it ineffective against external events that challenged multiple barriers simultaneously. The independence assumption underlying defense in depth was invalidated when external events created common mode failures across supposedly independent safety systems. The depth assumption was invalidated when barriers designed for sequential protection became sequential dependencies under station blackout conditions. Probabilistic risk assessment methodology, accepted throughout the international nuclear community as the scientific basis for safety regulation, was revealed to systematically exclude the most significant failure modes that caused severe accidents: institutional failures, human factors under stress, external events beyond historical experience, and multi-unit interaction effects were either inadequately modeled or excluded entirely from risk calculations. This meant that risk assessments provided false confidence in safety levels while systematically ignoring the factors that determined actual risk. The Fukushima accident demonstrated that nuclear safety required fundamental reconsideration of basic assumptions about accident scenarios, consequence assessment, and emergency planning. The beyond design basis conditions that caused the accident were not incredible natural events, but predictable consequences of design assumptions that ignored available geological evidence and regulatory processes that prioritized operational convenience over comprehensive safety analysis. Perhaps most significantly, Fukushima revealed that severe nuclear accidents create long-term societal consequences that extend far beyond the immediate radiological hazards that dominate safety analysis. The displacement of entire communities, the loss of agricultural and economic productivity, the psychological impact of uncertainty about health effects, and the erosion of public confidence in expert institutions represented consequences that were essentially permanent and largely irreversible. These societal impacts were not addressed in pre-accident safety assessments because they were considered outside the scope of technical safety analysis. The forensic evidence from Fukushima ultimately demonstrated that the nuclear safety paradigm accepted by regulators and industry worldwide was based on assumptions that could be invalidated by natural events that were neither unprecedented nor unpredictable. The institutional systems responsible for ensuring nuclear safety had systematically excluded from consideration the very conditions that made severe accidents possible. The technical systems designed to prevent and mitigate severe accidents had been optimized for scenarios that bore little resemblance to actual accident progression under beyond design basis conditions. The fundamental question posed by Fukushima forensic evidence was whether complex technological systems claiming ultra-high safety levels could ever be trusted when their safety assessments systematically excluded the institutional failures, human factors limitations, external event possibilities, and consequence uncertainties that determined actual safety performance. The gap between theoretical safety calculations and actual accident consequences revealed at Fukushima suggested that nuclear safety claims based on probabilistic risk assessment were fundamentally unreliable, not due to calculation errors, but due to methodological assumptions that excluded the most significant sources of risk from analysis.